Hello students, welcome to the next session of the All Force e-learning program. This session we will take up the applications, the mathematical applications, the problems, the identities regarding the effect of the dipole in the electric field. What happens? What are the applications of the electric dipole in the electric field? Suppose the applications of the electric dipole in the electric field, right? So we have learned in the previous episode that whenever a dipole is suspended in a uniform electric field, there is a uniform electric field E. So like this, these are the parallel lines, a uniform electric field. This denotes the pattern of the electric field, uniform electric field. A dipole is suspended. This is a dipole, an arrow. A bold arrow represents a dipole like this. A dipole is suspended at an angle theta. P is the dipole moment, E is the electric field. Then we have understood whenever a dipole is suspended in a uniform electric field, the net force on the dipole is zero. Dipole, positive charge of the dipole experiences force in the direction of the field. Positive charge is here in the direction. Negative charge is here in the opposite direction. So the net force of the dipole is zero. Resultant force zero, no translative motion. But these two forces acting at some perpendicular distance produce a turning effect. There is rotation effect, turning, torque. So the torque experienced by the dipole in the uniform electric field, tau, first question, tau is given as P bar cross E bar vectorially first. So the magnitude of torque mod tau is mod P mod E sin theta. This is the torque that is experienced by the dipole in the uniform electric field, Third, now the direction of this torque, it is perpendicular to the plane of the dipole moment and electric field. Dipole moment is this way, this is dipole moment, this is electric field. Then perpendicular to the plane, it is like this. In this direction the torque exists. So torque is along the direction perpendicular to P and E and passing to the midpoint of the dipole. Okay. Now coming to the factors affecting the dipole there. So tau depends on the dipole moment of the dipole. The stronger the dipole moment, more the torque. Stronger the field, more the torque. And the angle theta even. Right? So therefore, tau proportional to P, E and theta. Magnitude of tau 1 is P1 E1 sin theta 1. Magnitude of torque in the second case, P2 E2 sin theta 2. So therefore, tau 1 by tau 2 is P1 by P2, E1 by E2 and sin theta 1 by sin theta 2. Same dipole, P cancel. Same field, E cancel. Same angle, E will be cancelled. Theta will be cancelled like this. So the ratio of the fields under two different cases, tau 1 by tau 2, P1 by P2, E1 by E2, theta 1 by theta 2. Sin theta 1 by sin theta 2. Now, let us take up the different cases. What happens had this dipole been in the direction of the electric field? That is, there is a uniform electric field like this and our dipole is also in the same direction. So this is minus Q, this is plus Q. Our dipole is also in the same direction like this. P, both are in same direction. P and E are parallel. If P and E are parallel, same direction, theta is equal to 0, same direction, then what would be the effect? Well, I was telling you, positive charge will experience force in the direction of the field, negative charge experiences force in the opposite direction, both equal and opposite forces. So net force is 0, resultant force 0. Resultant force 0, no translatory motion, neither it goes forward nor backward, no linear motion. And now the angle, we know the torque is mod P mod E sine of the angle between P and E. But here P and E both are in same direction. The angle is 0, sine 0. But we know according to trigonometry, sine 0 is 0. So the torque is also 0. So torque is also 0 in the sense there is no turning effect, no rotational motion also. So no force no linear motion, there is no linear motion and no rotational motion. So the system, the dipole remains in equilibrium. Neither there is linear motion nor there is rotational motion. It remains in equilibrium. Right? Case 2. Now suppose if P and E both are in opposite direction, in the sense theta is 180 degrees. How does the torque and this force vary? So in the same electric field E, I am suspending the dipole, minus Q is here, plus Q is here. Now the dipole moment is in downward direction. So both are in opposite direction. The angle is 180 degrees. Again what happens? Positive charge experiences force in the direction of field, negative charge in the opposite direction. Both positive charge in the direction, negative charge opposite, both are along the same line and same this thing. Both are opposite, they cancel. So the net force is 0. No translational motion. And theta being 180, magnitude of the torque is mod P mod E sin 180. Again sin 180 is 0. So the torque is also 0. Even in this case also, the dipole will neither possess translatory motion nor rotational motion. This here also it is said to be in equilibrium. But these two equilibriums are different. We will learn about that in the just in the next thing. So force is 0, torque is 0. Neither linear motion nor rotational motion. Equilibrium. Third case, case 3. So if P and E are perpendicular, theta 90 degrees. A dipole is suspended perpendicular to the electric field. Suppose if this is the electric field and the dipole is like this, so dipole is perpendicular. In the first case, the field is like this, dipole is also in the same direction. So this is minus Q, this is plus Q in the same direction. So in this case, it neither moves forward nor backward, it remains as it is. It neither turns like this nor this way, it remains as it is. So there is neither linear motion nor rotational motion, it remains in equilibrium. In the second case, theta 180, this is the field like this, and our dipole is placed this way. Here also, the net force is 0, net torque is 0. So it again remains stable like this. It remains in equilibrium. There is no turning, no linear motion, no rotational motion, remains in equilibrium. Case 3, theta 90. If the dipole is suspended perpendicular like this, perpendicular to the field, this is positive charge, this is negative charge. Now positive charge experiences force here, negative charge experiences force here. Positive force on the positive charge acts here, force on the negative charge acts here, both equal and opposite. Now net force again, so if I draw the diagram, this is the field, our dipole is like this, minus Q plus Q, and the dipole moment is in this direction. Positive charge experiences force in the direction of field, negative charge in the opposite direction. Net force is again 0, so resultant force 0, no linear motion, no translator motion, it remains linearly, there is no motion. But torque, if I calculate, it's mod P mod E, the angle between them is 90. E and P both are perpendicular. E is like this, P is like this, 90. So it's sin 90. You know sin 90 is 1 according to trigonometry. So the magnitude of the torque is mod P mod E into 1. And this is maximum. So whenever a dipole is suspended in the electric field at right angle to it, it experiences maximum torque. There is maximum turning effect that is being produced on it. Right? Linearly there is no motion. There is high amount of rotational motion. Turning effect is more. So it turns like this. There is turning effect. So torque is maximum. A dipole experiences maximum torque when it is placed at right angle to it, perpendicular to the field, theta 90 degrees. It experiences maximum torque. Now from this even you can get the definition of dipole moment even. In this case, suppose let us extend this. Let the dipole and the electric field be perpendicular, and the electric field is of unit strength 1 Newton per coulomb. It is 1. Then what would be the torque experienced? So torque will be mod P mod E. E is 1. into sine 90, this is also 1. So magnitude of the torque is mod P. So now what is dipole moment? Dipole moment is equal to the torque. Dipole moment will be equal to the torque experienced by the dipole when it is placed in a unit electric field, in an electric field of unit electric field intensity at right angle to it. If theta is 90 and E is equal to 1, E is 1, theta 90, then whatever torque that is experienced is the dipole moment. The dipole moment of the dipole P bar is mod tau. A special case, please remember. So when the dipole is either parallel or anti-parallel, no torque. The dipole will not experience any torque. The torque experience is 0. But when the dipole is placed at right angle to it, 90 degrees, maximum torque is experienced. Highest torque will be acting on it. So maximum turning effect is being observed in this case. When theta 90, it is the highest torque like this. Right? Okay. One. Now, what is the work done? Let us evaluate a formula for the work done in turning the dipole in an electric field. Suppose, let me imagine a uniform electric field like this. Parallel lines, uniform electric field E. Right? So, I want to turn a dipole. There is a dipole minus Q plus Q. Right? This is the dipole AB at an angle theta. Now initially the dipole is along this field. Now I want to turn this dipole through an angle theta. So I want to produce a turning effect by applying an external force, external torque. If I want to turn the dipole against the field. Actually when a dipole is suspended in an electric field, the field tends to rotate it to decrease the angle between the vector. It tries to reduce the angle, tends to make them parallel. But if I have to turn it against the field, so what is the work done in doing so? So let the dipole moment, we know dipole moment is the length of the dipole is 2a, this is 2a, angle between the field is E, and this is the dipole moment vector, we know it is 2aq dipole moment. Now what is the work done in turning the angle, in rotating the dipole through an angle theta? Right, work done. Now let us recall what you have studied in your first year. We know the work done to move a system, displace a system is force F dot S. We know W is equal to, W work done is F dot S or Fs cos theta. This is for linear displacement. Suppose if I have to produce a torque, there is a rotation, then the same work done W is tau into theta. Tau is the angle, tau is the torque that is required to turn. To produce a rotation effect, there is torque, and the angle through which you want to rotate, it is theta. So work done is tau into theta, right? So here I want to produce a rotation effect. So the work done is to be taken as tau into theta, that is torque into theta. We know the torque acting on the dipole, we know the torque acting on the dipole is P bar cross E bar. That is mod of torque is mod P mod E sine of the angle between the vectors, two vectors. So let the dipole be at some angle theta. Now initially at some instant. Now at this instant, from this position, if I have to rotate this torque through a small, rotate this dipole through a small angle d theta, I want to turn it through a small angle d theta. Let's suppose initially it is at this position to the field. Now I want to tilt it through a small angle, a small little angle. Then the small work done in doing so, dW, is the torque acting on it at that position tau into the small angle d theta. So we know in general we have studied in first year, to produce linear motion the work done is F dot S Fs cos theta. To produce rotation effect, work done to rotate, turn, torque into theta. So at this position let the torque be tau at any instant. At this position the torque is Pe sin theta. and from that position I want to tilt this to a small angle d theta. Then the small work done, it is tau into d theta. So dW is equal to, let me substitute the magnitude of tau there. So it's Pe sin theta d theta. It is Pe sin theta d theta like this. So tau is Pe, magnitude Pe sin theta d theta. Theta is the angle at that initial portion. Now what is the total work done in rotating it from an initial angle theta 1 to theta 2? If you have to find the total sum of all the products, we have to perform integration. Whenever you come across such mathematical expression, you have to perform integration. So the total work done in turning the dipole from theta 1 to theta 2 angle, the total work done is W is integral dW. So this is equal to integral of dW is Pe sin theta d theta. The limits are theta 1 to theta 2. The limits are theta 1 to theta 2. So the total work done W is Pe sin theta d theta. So therefore the total work done W. Now in this integration term there, P is a constant. Dipole moment of a dipole is a constant. It does not change with its position. Electric field, we have taken uniform electric field. So these two are constants. Taking the constants out of the integration, Pe, integral theta 1 to theta 2, it is sin theta d theta. This is the thing there. Now coming to the integration part. In basic mathematics in first year, we have learned the integration, a simple integration. We know integration of sin theta d theta. Integral of sin theta d theta is equal to, it is minus cos theta. Integration of sin theta d theta is equal to minus cos theta. Suppose if you take limits theta 1 and theta 2, this is the upper limit, this is the lower limit. So it's minus cos theta between the limits theta 1 and theta 2. Now expanding, evaluating, first you have to substitute the upper limit minus the lower limit. So if I substitute, it is minus of cos theta to the upper limit, right, minus of now the lower limit. So it is, the term is minus cos theta 1. So it's minus cos theta 2, minus of minus is plus cos theta 1. So this is cos of theta 1 minus cos of theta 2. Doing the same here, performing the same integration here. This is the thing what we have learned in your basic maths. Performing the same thing. So the work done W is equal to P into E. Magnitudes of dipole and electric field are constant. So sin theta. Integration of sin theta is minus cos theta. So this is minus cos theta between the limits theta 1 and theta 2. Minus cos theta between theta 1 and theta 2. So substituting the upper limit and lower limit, work done is Pe of upper limit minus cos theta 2 minus of minus cos theta 1 like this. So the work done is Pe of, this minus of minus 1 becomes plus. So it is cos theta 1 minus cos theta 2. So the work done in turning, the total work done in turning a dipole from theta 1 to theta 2 in a uniform field E, the work done W is Pe cos of the initial angle theta 1 minus cos of the final angle theta 2. So work done is equal to W. Work done W is P. P is dipole moment. It's 2qa, right, into E, the electric field strength, cos theta 1 minus cos of theta. This is the work done in rotating the thing there. Suppose if you have to rotate turn the dipole from initial position. Suppose if this is the electric field, initially the dipole is in this position, minus q plus q, initial dipole. From here you have to turn through an angle theta. That is, initial angle theta 1 is 0 and final angle is theta. Theta 1 is 0, final angle is theta. Then substituting the work done, 2aq is P. So it's Pe of cos theta 1 0. It's cos 0 minus cos theta. We know according to trigonometry cos 0 is 1. So therefore work done is equal to PE of 1 minus cos theta. This is the work done in rotating the turning the dipole from the direction of the field, tilt it away from the field through an angle theta. Work done. This is the work done in turning the dipole from the direction of the field through an angle theta. It is initially in the direction of the field. Now you want to turn it through an angle theta. Then the work done is PE. P is dipole moment of the dipole. E is the electric field intensity into 1 minus cos theta. This is the work done in rotating in turning the dipole away from the field. If it is from theta 1 to theta 2, then the work done is PE cos of theta 1 minus theta 2, like this. Based on this, there was a very beautiful question in a previous entrance examination. He was asking a question like this. A dipole is initially, so let us remember this. A dipole is initially in the direction of the electric field, minus q plus q. Dipole is in this direction. Initially, a dipole is initially in equilibrium in the direction of the electric field. Now from that initial position, it is to be turned through an angle theta away from the field. So it is turned through an angle theta away from the field. The work done is W. To turn the dipole away from the field, if the work done is W, then the question is, find the torque required to maintain the dipole in that position. Suppose if you turn it and leave it, it again comes back to the original position, right? If you make a turn and you want to sustain that dipole in that position. So to maintain the dipole in that position, what is the torque required? This was the question that is being asked. So now we know generally what is the work done. Work done is PE into cos of initial angle theta 1 minus cos of the final angle. From theta 1 to theta 2, if you rotate, the work done is PE cos theta 1 minus theta 2. We are now rotating the dipole from the initial position. Initially it is in the direction of the field. Now from that position I am turning it through an angle theta. So the work done in turning it through an angle theta from the initial position, it's PE cos 0 minus cos theta. From 0 I am turning it through an angle theta. So the work done is PE of 1 minus cos theta. This is the work done. Now the question that is asked is, what is the torque required, external torque required to maintain that dipole in that position? Suppose if you just turn it and leave it, it will again come back to the original position. No, you want to maintain it. So you have to apply an opposite torque to sustain. So the external torque that is to be applied to maintain it in that is, we know the torque formula is P cross E. Mod of torque is equal to mod P mod E of sin theta. So the torque required to sustain, external torque that is required to maintain the dipole in that position, it's PE sin theta. Dividing both, PE cancel. This cancel. So reciprocating, the external torque by work done is sin theta by 1 minus cos theta. Right? So therefore cross multiplying, the external torque is W of sin theta by 1 minus cos theta. So this is the formula. This was the question that was asked in the earlier entrance examination. The external torque required to sustain a dipole in the final position after tilting it through an angle theta, the work done is W. Torque in terms of the work done W. So W sin theta by 1 minus cos theta. You can still even simplify this by trigonometry. We know according to trigonometry, sin 2 theta is equal to 2 sin theta cos theta. Sin double the angle, twice the angle is sin 2 theta. Sin 2 theta is 2 sin theta cos theta. So when this angle is 2 theta, here it is theta theta. Had this been theta, sin of theta, so if it is 2 theta here, you get 2 sin theta cos theta. If this itself is theta, so you have to take half the angles of this. That is 2 sin half of this angle theta by 2 cos theta by 2. So sin theta you can write as 2 sin theta by 2 cos theta by 2. Similarly, cos theta we know actually 1 minus cos 2 theta is 2 sin square theta by 2 sin square theta. So when this angle is 2 theta, here it is theta. If this itself is theta, 1 minus cos theta, when it is 2 theta, here you have to take half of this. But when the angle here itself is theta, this is 2 sin square theta by 2. So substituting in this, the external torque is equal to W of sin theta. Sin theta is 2 sin theta by 2 cos theta by 2 by 1 minus cos theta. According to trigonometry, 1 minus cos theta is 2 sin square theta by 2 it is. So 2 cancel, one of the sign is cancelled. So the external torque is W. Cos has remained, cos theta by 2 by sin theta by 2 has remained. Now cos by sin is cot. So work done, cos by sin, it is cot theta by 2. A beautiful earlier entrance examination asked based on this concept. A very good question, please remember, right? This is the relation between the external torque and the work done. Only work done in general work done is PE cos theta 1 minus cos theta 2. Initial angle theta 1 to final angle theta 2. Now if I am rotating this from initial position from theta 0 to theta, then the work done is PE of 1 minus cos theta. Right, so the torque is PE sin theta. Dividing both, I get, so work done is W sin theta by 1 minus cos theta. From this, you can even evaluate this, right? Okay. When an electric dipole is placed in a uniform electric field like this, an electric dipole in a uniform electric field P, and this is E, the potential energy U of the dipole, the potential energy is given as minus the magnitude of the dipole moment P, the magnitude of the electric field stem E, and cos of the angle between them. Right? So the potential energy of the system, potential energy of the dipole U is given as minus of magnitude of the dipole moment, magnitude of the electric field intensity, and cos of the angle between them. Like if suppose theta is equal to 0, then the dipole is in the direction of the minus q and plus q. The dipole is in the direction of the field, then the potential energy is minus PE cos 0. So it is minus PE minimum potential energy. At this position, the potential energy is the least, minimum potential energy. Now had theta been 180 degrees, the potential energy when the dipole is in opposite direction, minus q plus q like this, angle 180 degrees, theta 180. Now the potential energy is minus PE cos of 180 degrees. So it's minus PE times minus 1. So it's plus PE, maximum potential energy. In this case, the potential energy is maximum. Initially at this, when the dipole lies in the direction of the electric field, then the potential energy is minimum. When the dipole is opposite to the electric field, potential energy is maximum. Based on this, there was a very interesting question asked in the previous entrance examination. What is the work done to turn a dipole from this position to this position? From the position where the dipole is in the direction of the field. Suppose if this is the field, the dipole is in the direction of the field. Now from this position to the opposite, to turn it from this position to this position, what is the work done by the external agent? You know, work done W is equal to final potential energy minus initial potential energy, right? Or we know the work done formula, cos theta 1 minus cos theta 2. Right, from this also you get its final potential energy minus initial potential energy. Final is potential energy formula minus PE cos theta, right? Final potential energy cos theta 2. So minus PE cos theta 2 minus of minus PE cos theta 1. So we get it as PE cos theta 1 minus cos theta 2. So the work done Now the work done in rotating from this position to this position, from the position where the dipole is parallel to the field to the position where it is anti-parallel to the field. So it's PE times cos 0 minus cos 180. So work done is, it's PE times cos 0 is 1 and cos 180 is minus 1. So the work done is PE into minus of minus 1 plus 1, it is 2. It's 2 PE. The external work done, the work done by the external source in rotating it from the position where it is parallel to the field to the position where it is opposite to the field, it is 2 times P into E. P is the dipole, E is the electric field intensity. E is dipole moment and E is electric field intensity. Work done. This is also a previous entrance question. A very good question to remember there. Potential energy of the system. Potential energy of the dipole in an electric field is, it is minus P cos theta. So whenever a dipole is suspended in electric field, first point, the net resultant force is 0. Force on each charge will be EQ, equal and opposite. Net force is 0, first point. So no translatory motion. Translatory motion is cancelled. Second, the net torque acting on it when it is at a position theta, tau is mod P, mod E sine of the angle theta. P is sine theta. Third, the potential energy of the dipole at this position, whenever the dipole is at an angle theta, then it is PE cos theta. And the work done in rotating in turning the dipole against the field, opposite to the field, from theta 1 to theta 2 is cos theta 1 minus cos theta 2. So whenever a dipole is suspended in a uniform electric field, so the force is 0, torque is like this, potential energy P cos theta, this is P sin theta, this is P cos theta minus, and the work done is P of cos theta 1 minus cos theta 2. Right, thank you.